Hi everyone and welcome to Data Science with Marco. Today we are learning about classification and working with categorical variables. To do that, we're going to learn about three algorithms: logistic regression, linear discriminant analysis, and quadratic discriminant analysis. We're going to start off with a bit of theory and then we're going to apply all those algorithms in a project setting. Let's get started. We will start this tutorial with a bit of theory about classification. First, a bit of terminology. Binary classification is also termed simple classification, and this is the case when we only have two classes, for example, spam or not spam, or a fraudulent transaction or not. Of course, you can have more than two classes, for example, eye color, or you can have blue, green, or brown. So you see that in the context of classification, we have a qualitative or categorical response, unlike regression, where we have a quantitative response, or numbers. Now let's see how we can perform classification with logistic regression. Ideally, when doing classification, we want to determine the probability of an observation to be part of a class or not. Therefore, we ideally want the output to be between 0 and 1. Well, it just turns out that there is a function to do that, and it's the sigmoid function. As you can see here, when x approaches infinity, you approach 1, and towards negative infinity, you approach 0. The sigmoid function is expressed like this, and here we are assuming only one predictor. For now, we stick to one predictor to make the explanation simpler. With some manipulation, you can get this formula here, so we are trying to get a linear equation in x. Take the log on both sides and you get the logit. As you can see, it is indeed linear with respect to x, and most importantly, the probability is bound between 0 and 1. And now you can estimate the parameters with the following formula, but of course we will not be implementing these formulas ourselves. It makes sense that you want the predicted probability to be as close as possible to the observed state. For example, if your classifier says that a transaction is fraudulent, then that transaction should really be fraudulent. And just like with linear regression, we use the p-value to reject or not the null hypothesis. Of course, we can extend the logit formula to accommodate multiple predictors, and this will, most of the time, always give you better results since you are considering more predictors. So that's it for logistic regression. Let's move on now to linear discriminant analysis, or LDA. We want to learn about LDA because logistic regression has some caveats. When classes are well separated, the parameters estimate are unstable. They also tend to be unstable when the dataset is small. And finally, logistic regression can only be used for binary classification. With LDA, you can overcome these issues because it models the distribution of predictors for each class, so you can have more than two target classes. And it does so using Bayes' theorem. Bayes' theorem is explained like this. Suppose we want to classify an observation into one of k classes, where capital K is greater than or equal to 2. Then you let pi k be the overall probability that an observation is associated to the kth class. You let fk of x denote the density function of x for an observation that comes from the kth class. So this means that fk of x is large if the probability that an observation from the kth class has class capital X is equal to small x. Therefore, Bayes' theorem states the equations that you see. The probability of the class being k given x equals x is the ratio of pi k fk of x over the sum of pi l fl of x for all classes. The challenge here is really approximating the density function, so we will assume only one predictor and normal distribution. This is expressed by the function you see now. So if we plug this function in the formula we saw before and take the log, we find out that we must maximize this following equation. This is called the discriminant, and as you can see, it is a linear function with respect to x, hence the name linear discriminant analysis. When applying LDA, we need to be aware of the assumptions it makes and make sure that it applies to our situation. Here, LDA assumes that each class has a normal distribution and has its own mean, but variance is common for all classes. If you had more than one predictor, which should be the case, then each class is drawn from a multivariate Gaussian distribution, and each class has its own mean vector and there is a common covariance matrix. So basically, we must use vectors and matrices instead of single numbers, but the assumptions stay the same. Now that we understand LDA, QDA should be fairly straightforward. The main difference is in the assumptions. Just like LDA, we assume each class is from a multivariate normal distribution and has its own mean vector, but also now each class has its own covariance matrix. Therefore, the discriminant is expressed like this, and you see that the equation is now quadratic since you have two terms of x being multiplied together, hence quadratic discriminant analysis. QDA is better than LDA when you have a large dataset because it has lower bias and higher variance. But if your dataset is small, then LDA should be enough. Before we move on to the coding portion, we must understand how to validate our models in the context of classification. We use sensitivity and specificity. Sensitivity is the true positive rate, so the proportion of actual positives identified. For example, if we are to identify fraudulent transactions, then the sensitivity is the proportion of fraudulent transactions that are actually fraudulent. On the opposite, specificity is the true negative rate, or the proportions of actual negatives identified. So it will be the proportion of non-fraudulent transactions that are actually non-fraudulent. We can also use the ROC curve, where ROC stands for Receiver Operating Characteristic. We take the area under the curve, or AUC. That's why you probably hear about the ROC AUC. We want the ROC AUC to be close to 1. Why? Well, as you can see, we plot the false positive rate against the true positive rate. Ideally, we have a false positive rate of 0 and a true positive rate of 1, which would give an area under the curve of 1, and the curve would hug the upper left corner of the graph. So that's it for the theory. Let's jump on to the code. Alright, so let's start off with this project. Fire up your Jupyter notebooks. I have already mine open. As always, I have this folder called data, in which I put my dataset called mushrooms.csv. The link for the dataset is in the description of the video. So in this project, we are going to classify mushrooms as either being edible or poisonous, depending on different features. So you have cap shape, cap surface, cap color, etc. And I put all the possible values here at the beginning of the notebook. So let's start off by importing the libraries we are going to use. So pandas as pd, numpy as np, of course matplotlib.pyplot as plt, and also seaborn as SNS. Now we are going to import sklearn.preprocessing and specifically label encoder. You will see how that will be used later on. Also from sklearn.model selection, import train test split with underscores and also cross val score. Awesome. From sklearn.metrics, we are going to import the ROC curve and the AUC, as well as the confusion matrix. Shift enter. Oh, sorry. First, we're going to put the matplotlib inline so we can see our plots. All right. So shift enter. And now I am just going to to define a path for my dataset. So data/mushrooms with an s.csv. And now I'm just going to display the first 5 rows of the dataset. All right, so as you can see, these are our first 5 rows. We see the class, poisonous or edible, and then we see the values for each feature. So now I'm just going to do a plot to see how many poisonous and edible mushrooms we have in our dataset. So this will help us see if the dataset is balanced or not. So for that, I'm going to use seaborn. And as you can see, our dataset is fairly balanced. We almost have the same amount of poisonous and edible mushrooms. So that is very good. We're not going to have to do a lot of pre-processing for our analysis. Now I'm going to define a function that will allow us to see, depending on what feature, how many mushrooms are poisonous or edible. So for example, if I plot for the cap surface, so for all possibilities of values for the cap surface, I want to know how many of those mushrooms are edible and how many of those are poisonous. So that's going to give us a bit of intuition as to which feature helps you to actually classify your mushrooms. And that's it. So that's the function. Now I'm going to show you how you can use this function, but I am not going to run it because this will actually run for all the features of the dataset. So it's going to generate a lot of plots. So I'm just going to show you how to use it, and you can run it on your notebook if you want. So you set the hue equal to data class. So that means that you're going to have two colors, right? So one for poisonous, one for edible. And then you simply want to drop the class column and then plot the rest of the data. So to do that, you just do plot data, and then you pass in the hue and data to plot. So fairly simple, very straightforward. Like I said, you can run this function on your own notebook if you want to see the examples, but I will not run it for now. So let's move on to pre-processing. So you can do this by doing escape 2, by the way, and shift enter. So now I'm going to check how many null values do we have in our data sets, because we do not want any empty values. So for calling data.columns, I want to print the name of the column and then the sum of null values if they are null. So you do that by data call.isNull.sum. If you run it, that is amazing. As you can see, we have 0 everywhere. So that means that we have no null values in our data set. That's perfect. Now we are going to use the label encoder. So what label encoder will do is that it will transform our class column into 1 and 0s, because we cannot work with letters. We have to work with numbers, right? So you do le.fit transform data class. And now I will show you the result, data head, and there you go. Now as you can see, the class is now 1 and 0. So either it is poisonous or not poisonous. So 1 being true, 0 being false. Then you want to one-hot encode the rest of the data set. So to do that, we do pd.getDummies, and then you pass in the data. So let's see what the result of that will be. And as you can see, now we have added a lot of columns. So we went from 23 columns to 118 columns, because now for every feature, we have either true or false. And now that is perfect. This data is ready to be worked with because we have only numbers everywhere. So let's move on to modeling. First, I'm going to determine what the target variable is. So in this case, it is the class. .values.reshape -1, 1, perfect. And then the features is going to be the encoded data. .head, .drop the class column, axis equals to 1 to make sure that we drop the column. And then we're going to define a train and test set. So we do xtrain, xtest, ytrain, ytest is going to be equal to the train test split that we imported earlier. So you pass in your features, you pass in your target variable, and then you define the size. In this case, I'm going to do 0.2. So 20% of the data set will be randomly removed to use as a test set. And we're going to use the rest to train. You can set a random state, by the way, to keep the results constant. So let's apply logistic regression, our first algorithm for classification. So from sklearn.linear model, import logistic regression. Now we're going to initialize the model. So logistic reg is going to be equal to logistic regression. Now I will fit the model to our train set. So pass in xtrain and ytrain dot Ravel. Now we want to get the probabilities. So yprob is going to be equal to logistic reg dot predict underscore proba, and we're going to use the test set in this case because we fit before and now we are doing probabilities on the test set, right? And now we set our threshold to 0.5, so the actual prediction is going to be np.where. So in this case, if the prediction is greater than 0.5, we're going to say it's equal to 1, and otherwise it's going to be equal to 0. So this is really where we are classifying our mushrooms. So we have run that and everything is okay. You can safely ignore the warning on the screen. And now we're going to see at a confusion matrix. So the confusion matrix is actually going to show you how many mushrooms were correctly classified. So confusion matrix, you pass in y test and you pass in the y prediction. And hopefully if those are equal, you will see that we're going to have a diagonal matrix. And that is actually amazing. We have a diagonal matrix. So all poisonous and all edible mushrooms were correctly identified. So let's check that with actually another metric. We're going to use here the false positive rate and the true positive rate, as well as the thresholds, and we're going to set that equal to the rock curve. Pass in y test and y prob. And then the rock AUC is simply going to be equal to the AUC, and then you pass in the false positive rate and the true positive rate. So here we are actually going to use the rock curve. And as you can see, when we calculate the rock AUC, we get 1, which is again perfect classification. Now I'm just going to define a function to plot the rock curve so we can visualize it, see how it looks. So this function is going to take in the rock AUC, and here I'm just basically building the plot itself. So I'm just setting the figure size to 7 by 7. I'm setting the title to receiver operating characteristic. Then I am actually going to plot the false positive rate and the true positive rate. And I'm going to give it a different color here. I'm going to use red. We're going to give it a label called AUC. And I'm also going to approximate the AUC, basically. So this is going to give us approximated to the 2 decimal places. Then I'm going to give it a legend. I'm going to put it on the lower right side of the plot. Now I am also going to plot a straight line going through 0 and 1. This just serves us as a general guide to evaluate the rock curve. And I'm going to make this line dashed. Now I am going to define the axis, so PLT axis tight. Give some labels, so the Y label is the true positive rate and the X label will be the false positive rate. And that's it for our function. So let's actually plot the rock curve that we obtained above with logistic regression. And you should get the following. So this is actually a perfect rock curve. So it's hugging the upper left corner and we have an AUC of 1. So that means perfect classification. So now let's move on to our second algorithm, which is linear discriminant analysis. And let's see if the results are going to be different. Of course, it cannot be better, right? So from sklearn.discriminant analysis, you are going to import linear discriminant analysis. Now feel free to pause the video and try it on your own, because we are going to basically repeat the same steps as above, only this time we are using a different algorithm. So you can always pause the video and try it on your own as an exercise. So LDA is going to be equal to linear discriminant analysis. So here I'm initializing the model, then I'm going to fit the model with our train set. So pass in xtrain and ytrain.ravel. Then I am going to get the probabilities from the LDA model. So LDA.predict proba, and you pass in x test. And then you get the predictions, and we use the same threshold as before, 0.5. So it's actually going to be the y prob np.where y prob LDA. There you go. If it's greater than 0.5, we're just going to classify it as 1, and otherwise it will be 0. Run this cell, and awesome, everything went well. As again, you can ignore the warning on the screen. So now we're going to build a confusion matrix here. So ytest and ypred LDA. And let's display the confusion matrix. And as you can see, perfect classification again. So as an exercise, we will still build the ROC curve and show it simply to make sure that we get a ROC AUC of 1. So get the false positive rate, true positive rate, and thresholds to be equal to ROC curve. Pass in ytest and pass in the y probabilities here in this case, so y prob LDA. Now display the ROC AUC of LDA. So first you assign it false positive rate, true positive rate, and now we are ready to display it. So ROC AUC LDA, and we should get 1, and as expected, we indeed get 1. Now we are going to plot the ROC curve using the function we defined earlier. And as you can see, you get the exact same function, which is again expected, right? Because our confusion matrix was the same, the ROC AUC was the same, the plot should be the same. So again, LDA is a perfect classifier in this case. And finally, we are going to implement quadratic discriminant analysis. Again, I strongly suggest that you pause the video at this point and really try to repeat the steps that we have done before using QDA. So as always, we're going to import the model from sklearn. So from sklearn.discriminant analysis, import quadratic discriminant analysis. Now you set the model, so you initialize it, so QDA is quadratic discriminant analysis. You can always press tab, by the way, for autocomplete. You fit the model on your train set, and then you get the probabilities. Like I said, the steps are exactly the same, it's just that we are using a different model. So yprob QDA is QDA.predict proba, and you use the test set, of course. And then we get our classification. So np.where, use the same threshold. So if it is greater than 0.5, classify as 1, otherwise it is 0. Awesome. Run the cell and ignore the warning. Then we're going to take a look at the confusion matrix. So let's see if we also get a perfect classifier here with QDA. So confusion matrix, you pass in a y-test and the predictions. Displaying the confusion matrix, as you can see, we get the exact same as before. So again, QDA is a perfect classifier for our data set. Now we're going to plot the ROC curve and get the ROC AUC as well. So just like before, false positive rate, true positive rate, thresholds is going to be equal to ROC curve, pass in y-test, and the y probability, so y prob QDA. And then you use the false positive rate and true positive rate to get your ROC AUC. So here I'm calling it ROC AUC QDA. It's going to be equal to the AUC, pass in the false positive rate and the true positive rate. And now you can display the ROC AUC of QDA. And you get 1. Perfect, as expected. Now we are simply going to plot it to make sure that it looks like the other plots, and you know that it will. And it should, and as expected, perfect ROC curve AUC of 1. So that's it for classification. Thank you for watching the video. In the next one, we are going to learn about resampling methods and regularization. This is going to help us further improve our models, and will also make our data science workflow more robust. So stay tuned.